Hi everybody. This is last video which talks about this 11.4. So this is just, of course, an introduction to logical implication and equivalence, just to help give you better understanding to these equivalence and statements. And actually this a basic idea to help you with editing. For example, if you edit an essay, you will put a statement, but it may not be said the right way, and you can change it. The meaning will be the same, but its format will be better. So that's equivalent statements, right? So just tautology is a statement form that always has a truth value true. So kind of a review, if you check previous sections, tautology as always is a statement form that always has a truth value of true, right? Truth value of true, regardless of the truth values of the individual statement variables it contains. So regardless of what's involved, it has that. Contradiction is a statement form that always has a truth value of false. Contradiction, right? It has a truth value of false. 1 equals 0. Contradiction. So regardless of the truth value of the individual statement variables it contains, all right? So that's one thing to think about as you're closing this chapter. Then we also talked about logical equivalence. This is something I left to be discussed in class, and it's two statements forms that have the same truth tables. All right, so same truth tables. That's a short way of understanding it. I'll say it again. It's two statement forms that have the same truth tables. They're called, of course, logically equivalent. And, there are some examples to do and prove. So we can show this here by using a truth table, right? So for example, if you build, so let's show this here. So let's say if you have P and Q, and you fill in the table, this is true, true, false, false, right? Then we put the other scenarios for each one. So, and we covered, so you want to see the previous video, if P then Q, there is only one case where it's gonna happen. Maybe I need to rewrite this just to make it better. Let's rewrite these to make them better. So we'll give some space. Yeah, that's better. All right, so if P is true and Q, then, and Q is false, then this conditional here is going to be false. That's the only case where it is false. In others, so watch the previous video about it. All right, so now that's clear. So now let's go back to this, not P or Q. So P is true, not P, which is false. So if you do that for remaining not true, that's false, and not false, that's true, or Q is gonna take, so this is Q, true, false, true, and true, right? Okay, so we'll complete this table as trying to show this statement here. So not P. So let's highlight them so we can reduce a different color. So here is P. Here is not P, which is the opposite, right? So now for OR Q, this column will have the result of not P or Q. Not P is false, right? Or Q is true. So we need for OR, this disjunction, we need one of them to be true, or both of them to be true to get true. So and look at the next one. Not P, false, or Q, false. Our result is false. Not P, true, or Q, true. Both of them are true, so definitely true. Not P, true, or Q, false. One of them is true, the outcome is true. All right. So for AND we need both, but for this junction of P and Q, which is the OR, P or Q, for it to be true, it's either P is true or Q is true, or both P and Q are true. All right. And last thing to talk about is P and Q are logically equivalent. And we write it this way with this two-way arrow here. All right, whenever P, whenever they are a tautology, right? And I did give this review about tautology. And before I keep going into that, I'll explain the important part with this section, which is if you compare, so let's give these columns numbers here, this one, and this one, and this one as well. So it's 1, 2, 3, 4, 5. So if you compare, because I still need to show that part, if you compare 3 and 5, you'll see that they're the same, right? And that's what this question we need to show, right? And of course, we can also show, so this these are equivalent. So P and Q is equivalent to this other statement, right? And we can also show, using the truth table, that if we have P or not P is a tautology, and that P and not P is a contradiction. That's not, so this is not difficult to show, right? And you can follow after this here. I think this one is much better. So to show that why. I'll tell you here. The example of the essay I talked about is, for example, if Jay is caught smoking in the restroom, then he is suspended, right? That example of Jay. So now if I say the statement, Jay is not caught smoking in the restroom, or he is suspended from school, it has same meaning. So when we attempt to simplify complex English sentences or analyze logical arguments, it is often useful to express a statement from a different but equivalent way, right? And that's what we saw in this section. All right, so compare the two. And you can pause the video, write it down, and compare the two. If Jay is caught smoking in the restroom, then he is suspended from school. All right, and ask yourself, would you write it this way or write it as Jay is not caught smoking in the restroom, or he is suspended from school, right? So, as I reviewed in the tautology to be a statement from that the truth value regardless of the component statements. And, and I reviewed the contradiction to be false, right? So we denoted that, you can denote the tautology with T, and I defined the contradiction to be a statement form that has truth false regardless of the component statements. And you can abbreviate the contradiction with C, right? So if I go back to this example, can we show that? Of course, we can just do it here. It's not a big deal for this one, and true, false. All right, so it would be the other way, false, true. So or we need one to be true. That's that. And for and, you want both of them, right, to be true, P and not P, which so P and not P, so this is false. And the other one is false, right? So, which means if this is a tautology, then this is a contradiction, right? So no matter what the value of P, if this is true, then this is false, all right? I think there may be more to do, but this is something to discuss in class a little more and do some examples. And these can be overwhelming sometimes, but they are helpful to know these laws, just like you do in math. And De Morgan's laws are interesting as well here. And of course, you can do truth table examples to prove these or to show. This is a simple one, the nice one, double negation. Double negation makes it correct. That's it. Double negation of P just gives you the P statement. commutative laws, right? P or Q, Q or P, right? So I would recommend you go through these, understand more what each one means. There are some you'll often use, and there are some that may not use. And of course, the tautology and the contradictions are also showing here. And there are more statements to talk about. And the Morgan's laws are interesting as well. When you see that negation is brought inside parentheses, it changes the connective from or to end. So that's you see. So when the negation is brought inside the parentheses, right? You see, it changes or to end. That's very interesting, and vice versa as well. All right. So because this the Morgan's law is interesting, an example to negate a statement: the Earth's orbit is round, and a year has 365 days. Example. So. All right, so we're asked to negate this statement of the form. So if you see and, so that's the form that we have, right? So by the rule, if you apply 8b, the negation can be written: the Earth's orbit is not round, right? So let's clearly examine this so you understand the power of this work. So the Earth's orbit is round and a year has 365 days, right? So if you want to negate this and to say it correctly, Earth's orbit is not round, but look, or we didn't use and, a year does not have 365 days, or a year does not have 365 days. This is true whenever the original statement is false, right? So think about this. There are some more examples that we can talk about and explain. But I think as far as this section, you may not do more of these, but you can explore these logical equivalences and see how they work. And I think that's all for now. Thank you and enjoy. And if you have any questions, you can always email me. If you have a different instructor, you can also talk with your instructor about it. The videos, some of them are wanting details and some of them are kind of a review, and some talk about the essential parts because in summary, this is a course that you want to be curious about, you want to be interested in learning, and the more you are curious about and the more you are interested in, the better it is, the better understanding you're gonna have. And as you see, it's you get a wealth of knowledge, kind of like well-rounded, we can say it that way, well-rounded student, and you can talk about different things. And as a summary, the discussion of the chapters, they went from, the sets to the probability to the beginning of linear to linear programming. So there is a variety of things that you can apply. And if you have any questions, just let me know. Thank you.